So welcome to Electron 6 layer, and you are watching digital signal processing lecture series. And today in this lecture we will see some previous year questions of digital signal processing of academic year 2022-23. Okay. So in this lecture we will see all the short type questions. So basically there are 10 numbers of short type questions, each having 2 marks each. Okay. So let us begin our discussion. So why we take first question is that why we take the unit circle as a reference in Z transform. Okay. So Z transform is basically is doing the analysis of the this discrete time signals and the LTI systems in Z domain. Okay. So it is basically it will do the frequency analysis of the discrete time signals. Okay. So in this case, why we take the unit circle as a reference in the Z transform. Okay. So in the Z plane, any complex number is represented as Z equal to R into e to the power of j omega. Okay. So here R is the circle. Okay. The radius of this circle. So you can see for unit circle that R becomes 1. Okay. So we have Z is equal to e to the power of j omega. Okay. So this is exactly the frequency analysis of this discrete time signals. Okay. So when we evaluate the Z transform on the unit circle, so it becomes x of e to the power of j omega, which is the discrete time Fourier transform, or it is DTFT. Okay. So and for LTI system to be stable, that ROC, that is the region of convergence, that must include the unit circle also. For stable system, the ROC must include the unit circle. Okay. So this is the imaginary axis and real axis. Okay. So you can see that this is the R. R is the radius of the circle. So if R equal to, in this case, the actually R equal to 1. Okay. So this is the unit circle. So R equal to 1. So if the LTI system to be stable, this ROC of the transfer must include the unit circle. Okay. So that include the unit circle. So if Z is greater than 1, this is the ROC. Okay, this ROC, the system will be unstable. Okay, so you can write this way. So we are using this unit circle because the LTI system to be stable, that must include the unit circle, and also it will we use the frequency analysis of the discrete time signals. Okay, that is become the discrete time Fourier transform. Okay, this is our first question. So each question having the 2 marks each. Okay, so next one is here. Second question is here, differentiate between convolution and correlations of discrete time signals. Okay, so we have to differentiate the between convolution and correlations. Okay? So you can see the convolution actually it is a response of the LTI system. That is the it is given as y of n equal to summation of it, mathematically it is written as minus k to k equal to minus infinity plus infinity x of k h of n minus k. Okay, so this becomes the response of this LTI systems, okay, which is called the convolutions. So in case of correlations, you can see it is used to determine the similarity between the 2 signals, okay, or a signal and its delayed version. If we are using the autocorrelation, that is the signal with its delayed version. Okay, that is the autocorrelations. So if 2 signals are different, then it is that is the cross correlations. That is mathematical written as R of x y l equal to n is minus infinity plus infinity x of n y of n minus l. So if the two, this is called the means cross correlations. Okay, so if this is the autocorrelation, this mathematically would be written as x of n. Okay, that 2 signals are same. That is x of n minus l. This is called the autocorrelation. This is of R x x l. Okay, so anyway, so correlation can be of 2 types. One is a cross correlation, and another one is a autocorrelations. Okay. Similarly, the operation of convolution is commutative. Okay, so x of n convolve with h of n equal to h of n convolve with x of n. Okay, but in the correlation, this operation is not commutative. So R of x y l is not equal to R of y x l. Okay, so this is useful for filtering of digital signals, the convolution, and the correlations is used for radar, sonar, and digital communications in geology, etc. Okay, so these are the difference between the convolution and correlations. Okay, so our third question is that what is the non-recursive discrete time systems. Okay. So a system whose output at any time n does not depend on the past output. Okay, so you can see it does not depend upon the non-recursive system. It does not depend upon the past output, but depends on present and past input values. Okay, that is called the non-recursive systems. Okay. So y of n, it is the output of a system. You can see it is a function of x of n, which is the present input, x of n minus 1, these are the past input values. But it does not depend upon the past output values. Okay. So the non-recursive system has no feedback from output to the input. So there is no feedback from output to the input. This is not dependent upon the past output. That is means that it is not depending upon the past output values. Okay. Similarly, for example, you can see y of n equal to x of n plus x of n minus 1. This is example of non-recursive discrete time systems. Okay. So for LTI systems, that is the y of n equal, this is the non-recursive discrete time system. So this is the output equations. Okay. So you can say it is depend upon the input only. It does not depend upon the output. Okay. Past value of the output. Okay. So the non-recursive systems has the finite impulse response, that is the FIR. So it is used for in digital filters in communication and control systems. The non-recursive systems are always stable systems. Similarly, it has the low computational efficiency. So the transfer function actually it contains only zeros. Okay. So these are the means non-recursive systems. So we can write 3 to 4 points. Okay, because it is a 2-mark questions. Okay. So next one is here. List the characteristics of adaptive filters. Okay. So actually adaptive filters are non-linear filters which does not follow the, so any filter, any means system that does not follow the superposition theorem, it is non-linear. Okay. So adaptive filters are non-linear. So it based on the cost function. Okay. Mainly it is the mean square error. Okay. Similarly, it uses the recursive approach, LMS or RLS. Okay. So these are the approaches. This is the least mean square. It is the recursive least square. Okay. That learns from the previous errors to improve the performance. Okay. So the filter coefficients are not constant because they change with each iterations. Okay. So that it automatically updates its transfer function based on the signal conditions or environment. So these are the some characteristics of the digital, adaptive filters. Okay. So here the no prior knowledge is required, like we have done in autocorrect. Okay. Similarly, what is frequency wrapping? Okay. So you can see in the bilinear transformation. Okay. When we map from j omega axis to the unit circle in z plane, so it is avoid the aliasing of frequency components. Okay, this is basically we are using in IRA filter. So it is basically the one-to-one mapping. Okay, so it converts from S domain to the Z domain. So while doing so, this avoid the aliasings of the frequency components. Okay. So in this case, the mapping is non-linear and the lower frequencies in analog domain is expanded to the digital domain. So it is actually converting S domain to the Z domain. Okay. So here is the higher frequency has compressed. Okay. So this is because of the non-linearity of the tangent function. This is the tangent function we have in the bilinear transformation in IR filter. So you can see. So this will be there is a tangent function. So basically this is known as a frequency wrapping. This is due to the non-linearity of the tangent functions. Okay. So this is the frequency wrapping. Okay. So basically, in the this is the IR field system that basically convert from analog to digital domain or S domain to the Z domain. Okay. So while doing so, we have the non-linearity. This is the non-linearity. This nonlinearity because of the tangent functions. So this nonlinearity is called the frequency wrapping. Okay. So we are compressing the higher frequency components here. Okay. So next one is what is the convolution properties of DFT? This is discrete Fourier transform. So this is not you are going to prove. Actually, we have to define only. Okay. So what is the convolution property? So if x1 of n, the DFT endpoint DFT is your x1 of k, and x2 of n, the endpoint DFT is your x2 of k, then the convolution property says that x1 of n, the circular convolution. This is the circular convolution. So this is actually basically the circular conversion. Okay, this is a symbol for circular conversion. So it will be endpoint DFT will be x1 of k. It will be multiplied with x2 of k. Okay. So if we take the circular convolution of x1 of k and x2, this is x2 of n, x2 of x1 of n with x2 of n, its DFT endpoint DFT will be x1 of k into x2 of k. So this is the convolution properties of the DFT. We are not going to prove this because it acts only for defining the convolution property of DFT. Okay. Similarly, so draw the block diagram of 2-point DIT-FFT and 2-point DIF-FFT. So this is the decimation in time, this is the decimation in frequency. So we are going to draw the waterfall diagram of each. So 2-point DIT-FFT, first one you can see, this is the 2-point flow graph of 2-point DIT-FFT. So there are 2 points A and B. So corresponding outputs are, okay, this output will be A plus omega n to the power k. This is the total vectors. Okay, into B. Similarly, this output will be A minus omega n to the power k into B. Okay. So these are the outputs if I am using the 2-point DIT-FFT. Okay. So omega n to the k is the total vectors. Okay. So this is minus 1 because this is a minus. Okay. So we can write over here 1 also. Okay. It is 1 1 you can write. Okay. So this is basically the decimation in time. Okay. As Fourier transform. Similarly, if we draw the flow graph of decimation in frequency FFT, so we have is a 2 point. So 2 point means A and B are the 2 points. Okay. So we have in this output corresponding to the input A will be A plus B. Similarly, corresponding to the input B, the output will be A minus B all into omega n to the power k. Okay. So this is the flow graph of the DIT-FFT and DIF-FFT. 2 point. Okay. So next is here, how many number of complex additions are there in 8-point DIT-FFT? Okay, so complex addition you have to calculate. So what is the formula for finding out the complex addition? The number of complex addition in 8-point DIT-FFT is here n log 2 means n. Okay, so n we can see it is how many points are there. So we can take here the n equal to 8. Okay, so here the n equal to 8. So we can calculate over here. So 8 log 2 n. So it will be 24. Okay. The question asks for only the complex additions. This is formula is same whether we are doing DIF FFT or DIT FFT. The formula remains same. If the question asks for complex multiplication, that will be n by 2 log 2n. Okay. So in this question only the complex additions are asked. Yeah. Okay. If the question asks for complex multiplication, that will be n by 2 log 2n. So it will be divided by 2. That will be 12. Okay. So it is same as means DIT-FFT and DIF-FFT. Okay. So the number of complex addition will be n log 2n and the complex multiplication will be n by 2 log 2n. Okay. So similarly, find the Z transform of a unit step signal. So question asks for the Z transform of a unit step signal. So you know that the unit step signal is your x of n, it is u of n. Okay. So it is a discrete time. So we can see this is the Z transform. So minus infinity to plus infinity, x of n, z to the power minus n. So we can see here x of n equal to u of n. So u of n, what is u of n? So u of n equal to 1. Okay, that will be 1 for n is okay greater than 0. Okay, greater than equal to 0. So that is why we have taken it 0 to infinity. It is for less than 0, it is 0. So u of n equal to 0. So no need to write minus infinity to 0 or something like that. So it is 0 to infinity. So z to the power minus n. This x of n equal to 1. Okay. So 1 into z to the power of minus n. So it will be z to the power minus n to the power of n. Okay. So basically there is a formula. So it is a infinite series. So I can write as that is summation of n equal to 0 to infinity r to the power of n. It will be 1 upon 1 minus n, where r is mod r is less than 1. Okay. So here we are taking that z to the minus 1, that is less than 1. So I can write this is actually r. Okay, z to the power minus 1 equal to r. Okay. So it will be this series converges when z actually r is z to the minus 1. Okay. So it will be z to the minus 1 is less than 1. So it will be z is greater than 1. So that will be x of z will be 1 upon 1 minus z inverse. That will be z by z minus 1. Okay. So this is the z transform of a unit step signal. Okay. So if we take the means ROC, this is the ROC. Okay. So this is the ROC. Here A equal to how much? Here A equal to 1. Okay. So you can write over here it is 1. Okay. Here this is 1 because that will be the z minus 1. So it will be z equal to 1. Okay. So this is the ROC of the unit step signals. Okay. So it will be z is here greater than 1. Greater than 1. So this is the ROC. Okay. So next one, I think it is the last questions. So differentiate between the linear and circular convolutions. Okay. So let us take this linear convolution and circular convolution. So linear convolution, you can write as x of n convolved by h of n. This is the formula of finding out the linear convolutions. And where x of n is the input sequence, so having length is L, h of n is the impulse sequence having the length of m. Okay. Here the you can see in the circular convolution, so you can write over here there is a circle. Okay. So x of n, this is the h of n. So here also x of n is the having the length of L and h of n is the having the length of m. So you can see over here what is the length of the output sequence. The length of the output sequence in case of the means linear convolution equal to n equal to L plus m minus 1. Okay. So but in this case the length of the output sequence is the maximum of L of m, L comma m. Okay. So if we are taking suppose x of n equal to means 1 to 1, okay, and h of n equal to means 1 2. Okay. So what will be the output sequence length? It will be maximum of L and m. So this is L. The L equal to here 3, here m equal to 2. Okay. So the output sequence length n will be, in case of circular convolution, it will be 3. So if we are using the linear convolution, what is the length? So L equal to 3 plus 2 minus 1. So then it will be 4. Okay, you can see this length, output sequence length is 4. So here the output sequence length is 3. Okay. So the zero padding is not necessary in this case. So you cannot append zeros, but in this case you can append the zero. Zero padding is necessary. Okay. So you can see this length is your L. So you have to mean same the h of length will be same as x of n. That is why you have to zero pad, means you have to pad 1 zeros over here to make the length x of n and h of n both are equal. Okay. So you have to use zero padding over here. Okay, to make the both the sequence of length having the same length. Okay. So here the sequences are shifted linearly. In this case, the sequences are shifted circularly. Okay. So the sequence is non-periodic in case of linear convolution. In the sequence is periodic in case of circular convolutions. So it can be used to find the response of the linear filter. In this case, it cannot be used to find the response of the linear filters. Okay. So these are the all the 10 questions having 2 marks each. Okay. So reference are, these are the reference. Okay. So thank you for watching this video. In the next lecture, we will see the 6 mark questions. Okay, of this same session. Okay. So thank you for watching this video. If you have any doubt, please ask me in the comment section. Thank you all. Have a nice day.